Hi everyone. Today we are going to discuss the ruthenium molybdenum clusters, ruthenium molybdenum nitrogen complexes, and stretching frequencies of those complexes. To discuss this, the dinitrogen, right, has 14 electron density, and it is an pi acceptor and sigma donor, such as carbonyl ligand. Right, similar to the carbonyl ligand, dinitrogen also 14 electron moiety, and it is also has the pi acceptor and sigma donor nature. So we can expect the ligational characters as such the carbonyl. But the thing is, the dinitrogen is a sigma donor, strong sigma donor, but weak pi acceptor. Whereas we know that the carbonyl is strong sigma donor and strong pi acceptor. This slight difference from the carbonyl to dinitrogen makes that the dinitrogen has only very few number of complexes rather than carbonyl has bunch of complexes. The dinitrogen will have very few number of complexes only, right? So in which the ruthenium molybdenum clusters, ruthenium molybdenum complexes are very important, right? So ruthenium complex, when it come to the dinitrogen, uh, pentamine dinitrogen ruthenium complex, ruthenium 2 complex, is the one where the ruthenium exists the octahedral geometry. The 5 amines will go for 5 sides of the octahedral, and one of the site will be occupied by the dinitrogen, one of the dinitrogen's nitrogen, right? So thus the complex exists, right? And its dimer also it exists in exist the dinitrogen complex, the diruthenium complex. Decamine diruthenium dinitrogen complex. Like that, there are two ruthenium complexes uh, we can have in the nitrogen ruthenium complexes, and the molybdenum complex has dinitrogen molybdenum complex, and is also exists octahedral geometry where 4 coordination sites were occupied by the one of the macrocyclic compound, right? The macrocyclic compounds can be discussed in the next chapter, coordination equilibrium. In briefly, if we want to say the macrocyclic complex, what is the macrocyclic complexes? They are the huge moiety. Macro is nothing but size is large, micro is smaller size, macro is larger size, right? So here macrocyclic compound, right? So which nothing but the moiety will be in larger in size, and cyclic it has an and cyclic molecule, it is a cyclic molecule, right? So here if we observe that it has cyclic, right, and it actually 12 crown 4 thio compound it is, right? The name of the ligand which occupying the 4 sites in the molybdenum complex, that is an 12 crown 4 thio compound, and the other 2 sites of the molybdenum octahedral complex, 2 nitrogen moieties will be bounded, right? So that's how the molybdenum dinitrogen complex it exists. In ruthenium and molybdenum, the dinitrogen has terminal end-on terminal bondings only, right? If we observe in ruthenium ruthenium complex, mono molybdenum complex, it has end-on, both has end-on terminal bonding mode, whereas in the dimer ruthenium it has end-on bridging bonding mode, right? So that's how the ruthenium and molybdenum complexes, dinitrogen complexes. Let us come to the stretching frequencies of dinitrogen. The free dinitrogen stretching frequency, nitrogen to nitrogen stretching frequency is 2331 per centimeter. Free dinitrogen nitrogen to nitrogen stretching frequency is 31 per centimeter. When thus dinitrogen it complexed, when it complex with metal, the stretching frequency, nitrogen to nitrogen stretching frequency will fall down till 2100. In approximate of 2100 it falls down, right? So when it is further decreases, when the dinitrogen bridging two metals, when it is bridging two metal, the nitrogen to nitrogen stretching frequency in dinitrogen will further decreases till 1800, around 1800 it will fall down, like that. Why it has to happen is, in free dinitrogen it has bond order of triple. The nitrogen to nitrogen bonds are 3 in free dinitrogen. When thus free nitrogen, when it complexes with single metal in a terminal bonding mode, the nitrogen's constant trivalency make that the nitrogen to nitrogen triple bond order will be decreases, right? We know that the nitrogen will have trivalency, it can maximally forms 3 bonds. When thus, right, dinitrogen getting bonded with one of the metal, the nitrogen side will be have more than triple bond, right? Thus more than triple bond order will make decrease in nitrogen to nitrogen bond order, right? And thus decrease in nitrogen to nitrogen bond order will be reflect in decrease in the stretching frequency of nitrogen to nitrogen from 2300 change to 2100, right, in approximate. Same to that, when it dinitrogen bridging two metal atoms, same it happens that the nitrogen's trivalency, constant trivalency, make that the nitrogen to nitrogen bond order to decrease, and thus will reflect in the stretching frequency, decrease in the stretching frequency of nitrogen to nitrogen stretching frequency till 1800, right? That we can examine in examples, right, in complex examples, right? Ruthenium complex, what we have in the previous, this monomer ruthenium, it actually has stretching frequency of dinitrogen 2105 per centimeter, right? And dimer of it, where the stretching frequency of nitrogen to nitrogen has 1800, right? 1800. So which means that, right, in a monomer to dimer, the dinitrogen stretching frequency is getting fall down, right, getting decreased, right? This is due to, right, where here in the monomer only one of the ruthenium is binding with dinitrogen's nitrogen, one of the nitrogen side, where the one of the nitrogen's trivalency only affected, right? With respect of that, the bond order was decreased. Whereas in dimer, two rutheniums are bonding two nitrogen sides of the dinitrogen, where two nitrogens trivalency, constant trivalency will affect, where the triple bond of nitrogen to nitrogen will fall down in approximate of double bond, where the nitrogen to nitrogen double bond and this ruthenium to nitrogen single bond will stabilizes the valency of the nitrogen, right? Nitrogens of dinitrogen. So thus change in bond order, right, will decrease in the bond order will reflect in the decrease in the stretching frequency of dinitrogen in the complexes, right? In simple complexes it will be vary, it will be decreases from free nitrogens to simple complex, single complex, single metal complexes, and it further decreases to uh, diruthenium, right? Dimetal complexes, dimetal dinitrogen complexes, because in dimetal dinitrogen complexes it has bridging, and the two nitrogen sides of dinitrogen will binds with two metal side, and thus make to decrease in the nitrogen bond in very extreme extent. So far the decrease will be extremely, it happens in stretching frequency of nitrogen to nitrogen, right? So same when we express a data, right, when we have a data of monomer of ruthenium complex, right? Here when we change the primary coordination sphere, right, this is what the primary coordination sphere, isn't it, right? So thus primary coordination sphere also is affecting the stretching frequencies. Why it is affecting, let us know. Different primary coordination sphere, pentamine, dinitrogen, ruthenium 2 complex, when we consider with all different primary coordination sphere, right, where you observe all the complex pair was same five amines in coordination sphere, same single dinitrogen ligand in the all the five complexes. The metal is also the same, and the metal charge also same, right? Here chlorine 2 nothing but ruthenium will have coordination pair of charge of +2, here +2, here +2, here +2, here +2, all will have same coordination pair charge and metal charge. All the complex pair was same, but where the change we observe is in the primary sphere, right? In the first complex it was uh, two chlorines, in the second complex two bromines, in the third complex two iodines, in the fourth fifth are they are a bulge anions, right? Trifluoroboride and hexafluorophosphite, right? So in this the stretching frequencies of nitrogen to nitrogen when we observe, and stretching frequency to metal to nitrogen stretching frequency also when we observe, right? The first complex stretching frequency, nitrogen to nitrogen stretching frequency is 105, sorry, 2105 per centimeter. In second complex 2114 per centimeter. In third complex 2124 per centimeter. In third complex 2144 per centimeter. In fifth complex 2167 per centimeter, right? Gradually from top to bottom, what happening, the stretching frequencies are going on increasing, right? In metal to nitrogen stretching frequency when we observe, the first complex has 508 per centimeter, and second complex has 498 per centimeter. In third complex 489 per centimeter. Fourth complex 481 per centimeter. In fifth complex 474 per centimeter, right? So here when we observe the stretching frequency of metal to nitrogen from first complex to last complex, fifth complex, it has going to be decrease. It is having the decrease order, right? Whereas the nitrogen to nitrogen stretching frequency was increase from top to bottom, first complex to last complex. When we observe these two things, right, they are the decrease increase of nitrogen to nitrogen and metal to nitrogen stretching frequencies are reversed one to other. This is known to us, right? Why it has happened, right? When metal to nitrogen bond order go on increases, its nitrogen to nitrogen triple bond order will be go on decrease, right? Isn't it? When metal binding with nitrogen dinitrogen's nitrogen, when the metal to nitrogen bond getting strengthened, when gets strengthened, the nitrogen to nitrogen bond will go on weaker, becomes weaker. That means the metal to nitrogen stretching frequency bond order, when it is increasing, the nitrogen to nitrogen bond order will go on decreases, right? Vice versa, which means the metal to nitrogen bond, when it is weaker, nitrogen to nitrogen bond will become strengthened, right? Which nothing but metal to nitrogen bond, when it is bond order is going on decrease, nitrogen to nitrogen bond order will go on increases, right? It is just reverse from these two to these two, right? This is the same will be reflected in stretching frequency. We know that the bond order is directly proportional to stretching frequency, right? So with that effect, here the reverse we are seen, right? So why it has to happen actually? Let us express in the complexes. The just change from one complex to a fifth complex, the primary sphere change will reflecting all these variation in nitrogen to nitrogen stretching frequency and metal to nitrogen stretching frequency. The primary sphere, when we observe from first complex to last fifth complex, the sizes of the primary complexes are go on increasing, right? Here till third they are just add ions, simple single atom ions, whereas the third and fourth they are molecular ions, which nothing but the sizes are go on increasing, right? Chlorine to bromine size will increase, bromine to iodine size is increased, iodine to this difluoroboride, the size of the it is becoming a molecular ion, so the size automatically will go on increases, right? So from the fourth to fifth, again the size of the primary sphere is much more larger, right? So like that, from first complex to last complex, the primary sphere's size is going on increasing, and that is the one. And the second thing what we have to observe is the electronegativity of first primary sphere to first complex primary sphere to last complex primary sphere. In first complex we have chlorine, by next we have bromine, by next we have iodine. Like that, when we go on, thus we see one first to last, the electronegativity of the binding site in the primary sphere to metal is go on decreasing, right? Here chlorine, bromine, iodine, these are boron and phosphorus will binds with the ruthenium in electrostatic bond, right? So all this, the electronegativity of all these binding sites with metal is go on decreasing in the primary sphere. So thus, right, electronegativity decrease and size increase will make the weaker bond, from the ruthenium to primary sphere from first complex to last complex, right? What I mean to say that in ruthenium to chlorine there are stronger bonding it may happens with comparatively with the second, where ruthenium to bromine, because the bromine size is more and its electronegativity is less. Due to that, the polarization of primary sphere to metal will be very decrease will be. So that's how the chlorine to ruthenium bond and bromine to ruthenium bond, and like that all from first to last complex, what happening, the primary sphere size is increasing, electronegativity is decreasing, will make the weaker bond from first complex to last complex, where the first complex will have stronger bond. Why? Because the chlorine is very high electronegative with compared to all the other, right? And its size of the primary sphere is lesser than all the other complex, where so far the chlorine will polarizes the ruthenium in a very high extent. It has closer bonding with ruthenium, right? So when it is having closer bond, right, it can grab the two electrons, right? All will have +2 charged, right? Ruthenium all here will be in +2 charge, which nothing but two electrons will be grabbed by the primary sphere. Thus electron grabbing capacity from first primary sphere to last fifth primary sphere, it's go on decreasing, right? Since the size increase and electronegativity decrease, right? Here the chlorine has smaller size and high electronegativity. So far it can effectively grab the two electrons from the ruthenium, right, and polarizes the ruthenium in very full effectively, and the ruthenium will have exactly +2 charge, right? Full polarizes and it has +2 charge, effective +2 charge, right? Whereas in bromine complex, right, bromine primary sphere complex, the bromine is larger size compared to chlorine, and its electronegativity is getting decreased from the chlorine side. So the electron grabbing capacity from ruthenium to bromine will be slightly decreased with when we compare to with chlorine complex, right? So what happens when it is electron grabbing from ruthenium to bromine is getting lowered, right? The effective bonding from ruthenium to bromine will be get lower, and its charge on ruthenium +2 will be go on slightly weaker charge it exists, right? Same to that, when it come to an iodine, it further polarization of ruthenium by iodine will be further lower. The charge on +2, charge of ruthenium +2 will be further weaker, right? Like that from top to last, right? The bond from the metal to primary sphere and the polarization of ruthenium complex will be go on decrease, right? So that effectively, when that it happens, right, ruthenium here having effective +2 charge, nothing but two electrons, loss of two electrons is very effectively happening. So it can bind with dinitrogen with an larger effectively, since when there is an electron deficiency on ruthenium is very effective, it can grab the electron density from the ligand set effectively, right? So having two electron loss in the ruthenium complex, chlorine ruthenium complex is very effective. So the loss of two ruthenium will be gained from the dinitrogen ligand side. So the effective bond can expect in the chlorine complex ruthenium to nitrogen, effective bond can be expected in chlorine complex, right? The stronger bond, effective bond nothing but stronger bond from ruthenium to dinitrogen happening. So metal to dinitrogen bond is very strong, right? So far we have highest metal to nitrogen stretching frequency in the first complex, right? So when there is a stronger bond from the ruthenium to dinitrogen in the first complex, that effectively nitrogen to nitrogen bond order decrease it happens. So when it is decrease it happens from nitrogen to nitrogen bond order, same effectively the stretching frequency will decreases. So have least stretching frequency for the first complex of nitrogen to nitrogen stretching frequency, right? So coming to last complex, let us discuss into the last complex. Having larger size primary sphere and the lesser electronegative site of the primary sphere make polarization on ruthenium is very weaker, right? So which means that two electrons cannot be effectively grabbed by the hexafluorophosphine moiety. So when it is not accepting the two electrons effectively from the ruthenium, the electron deficiency on ruthenium will be slightly weaker, right? The deficiency is weaker. So when there is a deficiency on ruthenium is very very weaker, right, the metal to dinitron metal to ligand bond, metal to dinitron ligand bond will be very very least effective, right. The bond will be very very weaker, since the ruthenium cannot be accept that effectively from the nitrogen side, right, since its electron deficiency is very very weaker with respect to of primary sphere, right. So when ruthenium having lesser electron deficiency, it cannot effectively bind with the dinitron. So metal to ruthenium to dinitron bond will be weaker bond, it happens here, right. When weaker bond in the last complex, the metal to nitrogen bond, when it is weaker with it, it's effectively the metal to nitrogen stretching frequency will be leaster in the complex of fifth, right. And when there is a metal to nitrogen weaker bond it existing, nitrogen to nitrogen triple bond order will be strengthens, right. So when it is strengthened, the nitrogen to nitrogen bond order will be very very larger. So when it is larger nitrogen to nitrogen stretching bond order, it effectively the stretching frequency will be also larger. So far the larger nitrogen nitrogen stretching frequency we will observe in the fifth complex, right. So that's how the stretching frequencies of the metal nitrogen complexes and the metal nitrogen complexes structural aspects we can express, right. So next we will be discuss the nitrogen fixation.